Well, hello and welcome. In this video, I'll be covering section 1.6, which is over the concept of continuity. My goal for you by the end of the video is to be able to determine the continuity of functions, as well as being able to determine the continuity of functions on a specifically closed interval. So let's start with the definition of what is continuity. We do have to kind of set the table a little bit, so reading through this statement right here, we have to have some value c that falls on this open interval a to b. We have to define some function f whose domain contains that open interval a to b. And in order for f to be continuous at that point c, we have to have, number one, the fact that when I plug c into the function, I actually get an answer back. So in other words, it's a defined value at c. And then we need to check both the left and right side limits as x approaches c and make sure that it has two values that actually agree with one another. In other words, that limit as I approach c without thinking one-sided limits actually exists. So again, the left side and the right side agree. And notice our third statement here is essentially just take those two conclusions that I got from number one as well as number two and just make sure that they actually equal the same value. So for example, if f of c came back as, I don't know, let's just make up some number. So let's say f of like 1 was equal to 2, and then in step 2 I figured out the limit as x approaches 1 of that function, f of x actually equals 2 as well. If these two numbers agree, then I can then say that at that value of 1, the function is continuous. And what we can say at the very end here is if f is continuous on every point inside that interval of a to b, then we can say it's continuous on that entire interval a to b. So it has to be true for every single point. So what we would look for with a continuity type question is any of those domain restrictions, such as do I need to get rid of any numbers because of division by 0, or do I have maybe half the number line or part of the number line that I needed to eliminate because of taking a radical of, say, a negative number. So what's nice with a couple of the types of functions that you've had from your past, polynomials and rational functions, we can actually make some generic statements about these that will actually be helpful when it comes to identifying or answering any question that deals with this concept of continuity. First one being all polynomial functions are continuous at every single real number, which hopefully that's not too big of a stretch because every polynomial you've ever graphed has been able to go forever left and forever right, and you could sketch the graph of it without having to pick up your pencil. A rational function, on the other hand, I need to be very mindful of what the domain is. So rational functions, remember, are any function with a polynomial in a numerator and in the denominator. So anything that makes the denominator equal 0 would be something I would leave out of the domain. So it would be at those numbers that make the division by 0 happen that I would be able to say that it must not be continuous at that value. So some examples here at the bottom. Letter A, f of x equaling x cubed minus 2x squared plus 4x minus 8. That all together is a polynomial. Since that is a polynomial, that statement, or the first statement we can say, is it's continuous everywhere. So we could also use interval notation and just say that it's continuous on negative infinity to positive infinity, that open interval, because every real number it happens to be continuous at. For letter B, where f of x is equal to x squared minus 4 over x minus 2, we can hopefully immediately think the domain of this is x cannot equal 2 because that would make division by 2 happen on the bottom. So I would be able to say it's continuous on the two intervals that creates, which would be from negative infinity until I get to 2, and then pick up on the other side of 2 and go on till infinity. I know it would be continuous on those two intervals. The only place it would not be continuous would be at that value of 2 because that was not a part of the domain. So with that last example, where it was not continuous at a specific value. In that case, it was x equaling 2 was the discontinuity. We'll go ahead and talk about what that really means. So a discontinuity is essentially any place where, say, our function is defined on the interval, except potentially at some value. In this case, we're just using c as that value. If it happens to not be continuous out there, meaning it does not fit the three necessary things for the definition, then we say it would have a discontinuity at that number. The two different types of discontinuities we have are one that's called removable and another one that's called non-removable. So specifically, a removable discontinuity is one where essentially if all I had to do was redefine this function at that value, and that would then make it such that it was continuous. For example, if I had a hole in the graph, all I would have to do is redefine that hole to actually be a part of that that function. So I could maybe turn it into like a piecewise where all I had to do is at that specific number say that its value was whatever the two limits from left and right actually equaled. We would call that then a removable discontinuity. So the example that we had on the previous page of f of x equaling the x squared minus 4 over x minus 2, that discontinuity, because I could then factor the top and the bottom. This is just kind of trying to prove why it would be a removable one, is the x minus 2's actually cancel out, giving me x plus 2 as really what that function is, which would essentially be, if I were to sketch a graph of it, a line right there, but it would just be undefined at that positive 2 value. So positive 2 plus 2, that would be up here at 4. There would be just an open hole right here. So if all I had to do was just say, well, let's just let f of 2 equal 4, that then would fill in that hole, and now it would be defined everywhere. Hence why that would be considered a removable. So it's essentially all removable discontinuities are those concept of holes that hopefully we remember from our prior class. Whenever you have a rational function that has a common factor on top and bottom, that's usually where a hole existed. A non-removable, on the other side, or on the other hand, is essentially if I can't actually just define a single value for that function of c, at that point, if it does not make it continuous, I would be able to say that that's a non-removable discontinuity. So that would be, if I had to maybe just make up an example on the fly here, if I said like f of x equaled 1 over x, if I were to think of the sketch of that graph, that would be the rational function, or sorry, what is that called? The reciprocal function. There it is. I knew I could remember it. But essentially, it would be passing through this 1, 1 and negative 1, negative 1 point, and then have the horizontal asymptote of y equals 0 and a vertical asymptote at x equals 0. There's no way, because of that vertical asymptote that exists right here, that even if I just picked a random y value along that, it still would not connect this bottom part right here. It would never connect this part of the graph with the other part of the graph, no matter what point or what value I gave for f of 0. It still would be spiking down and spiking up on the other sides. So hence, that's why we call that non-removables. I could not ever connect those two things, even if I defined, say in this case, f of 0 to equal some number like, I don't know, 1 would be, I guess, close to where I just plotted this example point. Even if I defined it there, there's still no way that that would connect those two sides of the graph. So let's move on and talk about continuity on a closed interval. So all the examples I had before were open intervals, meaning it did not include the endpoints. It just went on forever in both directions. Or again, it was just an open circle on each end, so it would be an open interval. In this case, we can talk about continuity on a closed interval, where I just would have to, again, set the table here and say that I have some function f that's defined on the closed interval, meaning the endpoints are defined, and it does not go on for forever. Then f, if we know that f is continuous on the open interval, meaning I don't worry about the endpoints, but I actually do the one-sided limits So as I approach a from the right, if that actually just equals what the function is for a, because again, our initial part was f was defined on that closed interval, so that means f of a should exist, just like f of b should exist, since again, that's the idea of being defined. And we check the second limit here as I approach b from the left, and that actually equals the function at f of b. I can then say that f would be continuous on that closed interval. So it's really just guaranteeing that those endpoints actually are defined values instead of open circles or going on for forever. What we can also go on to say is that f would be continuous from the right at a. Again, that's what the idea of this limit in this area is talking about. It's continuous from the right of a, or we could also say it's continuous from the left of b, using that second limit. So if we use kind of this concept or this definition of continuity on a closed interval, let's go ahead and just discuss with an example here what the continuity of this function f of x being equal to the square root of x minus 2 would be. So for this one, I know definition, or sorry, not definition, but domain of this one is going to be every number that is 2 and above should give me positive values inside, so I would be defined on that entire interval. And since it's defined on that entire interval, and I've already established that open is okay, but I'm really just focused on the closed part of this one, I just need to essentially verify that the limit as x approaches 2, and since I'm coming or it's defined to the right of that, I would want to come from the right of 2 of that function. I just need to make sure that that's going to agree with what f of 2 actually is. So if I plug in 2 to that, I'd get 2 minus 2 is 0, square root of 0 is 0. If I were to do, say, like a numerical approximation here, as I approach 2 from the right, that would be like doing 2.1, then getting closer at 2.01, and then 2.001. If I were to actually get closer and closer to 2, we would notice that the values of those actually would all slowly get closer to 0. And you could go ahead and try plugging those into the calculator and actually figuring out what those values are, but hopefully you can take my word for it that as I plug in those numbers, they still would be defined because they're greater than 2, and that would keep the inside positive, but as I get closer and closer to those values, they get smaller and smaller and smaller, which then would approach 0. Again, you could prove that using a calculator. You could also use the shape of this graph being shifted to the twice to the right, and then just being that kind of half sideways parabola going that direction. As I get closer and closer to 2, the y value should be getting closer and closer to 0, and that's defined at 2 to be equal to 0, so I can then say that this happens to be continuous on that closed interval on the left side of 2 until the open part, which is infinity. And I can also, with this, go ahead and say that it technically is also continuous from the right of 2, if I really needed to go into that much detail. So continuous from the right of 2. So those would be essentially my two statements that potentially, since all this said was discuss the continuity of this, those would be my two possible statements that I could say. It's either continuous on that, I guess that's really a hybrid, it's not open or closed, but including 2 up until infinity, or I could say it's continuous from the right of 2. So we'll go ahead and try a couple more examples before I end this video. So this first one here, I'm going to discuss this continuity of now a piecewise type function. So what is nice about the two parts of this piecewise is x plus 2 and the 14 minus x squared are both polynomials. And since they're polynomials, I know that on those intervals that it should be continuous on the include -1 until 3, but don't include it. And I know it should be continuous from include 3 until I get to 5. and also include it. Again, that's just taking the definition part that's over on the right and just saying, since they're polynomials on those kind of smaller intervals, I know that they have to be continuous because, again, they're polynomials. The only number in question, as you can see, would be this, what's happening at 3? So what I would need to do is just figure out what are those two limits as I approach 3. So if I approach it from the left, that would be the less than side, so that would be what's happening for the x plus 2 function. Well, since that's a polynomial, as I get closer to 3, it should just be the same as just plugging 3 in, so that should approach 5. If I do the limit as x approaches 3 from the right, now I would use the other part of that piecewise, which is the 14 minus x squared. Again, that's a polynomial, so I can just do direct substitution instead of having to worry about the plugging in decimals. If I plug in 3, I'd get 3 squared. 14 minus 3 squared, which is 9. 14 minus 9 would give us 5. Since these two numbers agree with one another, and we then can also look at what happens at the defined value. So f of 3 would be just plug into that bottom equation, which is exactly what we just did. That's not 9, it's 14 minus 9, which would be 5. All three of those numbers agree with one another, so it fits the definition that f of 3 is defined. It also fits that the limit as I approach 3, since the left and the right, which we just found earlier, were both equal to 5, that the limit as I approach that function, or sorry, of that function as I approach 3 is equal to 3. And since our third statement is, or not equal to 3, it's equal to 5. I need to stop writing and talking at the same time here. So it's equal to 5, and we know that f of 3 is also equal to that 5. We can then, by definition, go ahead and say that it would be continuous on that particular, I guess, closed interval here. So it's continuous altogether from the very beginning of what this function is defined at, which would be -1, until I get to the very end, which would be positive 5. And again, it was the only number in question was the 3, because that's where the function switched. I just needed to truly verify that it was continuous still at that number to be able to say that the entire interval was actually continuous. So now I'll move on to the last example, which is going to be close to the same as the last problem in your homework. But with this one, what we're going to do is have some piecewise function be defined, but actually have some coefficients that I potentially need to solve for to force that particular piecewise function to be continuous. So notice it's just saying that you have two constants, a and b. I just need to find what values of that would guarantee that it stays continuous for the entire real line. So notice this does go on. It's an open-ended one because x is less than or equal to -1 would imply I go on to negative infinity, and x is greater than or equal to 3 implies that it goes on to positive infinity. So it does go forever in both directions. I just need to basically look at the places in question. The place in question is going to be what's happening at -1, and then also what's happening at 3. Is there some form of jump or asymptote or hole? I just need to find some way to make it such that the ax plus b here in the middle picks up at 2 initially and then stops when I get to -2, such that it then would be continuous. So our way that we can approach this is, as we know, as we approach -1 from the left, since y equals 2 is just a horizontal line at 2, that value should come back as 2. And so I just need to make sure that since that y value ends at 2, that the beginning of the second one, when I plug -1 in for x, actually yields a value of 2. And then we can do kind of a similar approach for what happens at 3. Well, as I approach 3 from the right, I'd have this value of -2, because again, that's just a horizontal line at y equals -2. I just need to make sure that the end of ax plus b, but this time it's going to be when I plug in 3, actually comes back as -2. So it would be a times +3 this time, that then would equal that. So if I simplify those two expressions here, I'd end up with the first one being 2 is equal to a -a plus b. And then the second one I would have is going to be -2 is equal to 3a plus b. This hopefully is now ringing the bell of I probably need to use a system of equations to actually solve this. It looks like to me I have the b values already matching, so if I were to just take and subtract the bottom expression from the top expression, I'd end up with 2 take away -2, which would really turn into 4. I'd have -a take away 3, which would be -4a, and then b minus b would turn into 0. That should now allow me to solve for a by just dividing by -4, which then would give me a must have a value of -1. And then what I can do with that info is pick either of these two expressions and just plug that -1 in for that a value. So I'm just going to take the top one and just do, let's plug -1 in where a was, and let that be how I would solve for b. So in this case, double negative would make that +1, so I'd want to subtract that over, and I'd get +1 is equal to b. So the values of a and b, such that I want to make this, I guess, be forced to be continuous, would be those two values. Or I could go back and say that this middle expression right here really should just be -x plus 1. Again, just by replacing the a with -1, that gives me -x, and replacing the b with +1, that would give me +1. That would give me what that middle expression would have needed to be in order to be continuous on the entire real line. So hopefully this video has been helpful. Hopefully it was a little bit faster than the other ones. Sorry if I went through too quick, but as always, if you have some questions as you work through the homework, just reach out and let me know, and I'll do what I can to make it make sense. Again, I appreciate the time for you guys watching this video, and I guess until next time, we'll catch you later.